This is where we left off last time, right? Thinking about the amount of work our code was doing. When we were doing a linear search, just to review, when we were doing a linear search, like when we're writing algorithms and we're analyzing algorithms, we're asking the question, is my algorithm better than another algorithm? What we really care about is, well, like how much work is being done. You could have two algorithms that look wildly different, but are ultimately the same amount of the same amount of work computationally. So maybe we don't really care which one's better. Maybe as far as I'm concerned, they're basically the same in terms of goodness. And these questions is a big part of computer science, a big part of writing code to solve problems, is thinking about, well, is my solution even is my solution even reasonable to run? And I think we talked about this a little bit before. Did I ever talk about the traveling salesman problem? So here's a very interesting problem. Let's say you have a number of cities, okay? Maybe you have Antigonish, Port Hawkesbury, New Glasgow, Truro, Guysborough's over here somewhere, Halifax, I don't know, what else is in this area? Not much, right? Sydney's up here somewhere, let's just say it's over there, right? And let's say here's you, right? You're right here. And your job is you need to visit all these cities. You start in Antigonish, and you got to visit all these cities, and you want to start and end in Antigonish, and you want to minimize the total distance traveled. And what do we have here? We have 1, 2, 3, 4, 5, 6, 7 different cities to hit. I mean, one's kind of like a gimme. We're starting in Antigonish, and we want to end in Antigonish. But if I tell you to visit all these cities, what order are you going to do it in? Well, I mean, you as a normal human's probably go well, I'll probably do something like this, right? Right? Seems reasonable. Right? I mean, it would be foolish to go well, from Antigonish, I'm going to go to Sydney. And then from Sydney, I'm going to go to Halifax. And from Halifax, I'm going to go up to Port Hawkesbury. Then from Port Hawkesbury, I'm going to go to Truro. That's ridiculous. But at least, I mean, it is a valid solution in terms of yeah, okay, it'll work, you could do that. But the goal is not to find a path. It is to find an order. In fact, this is mathematically, it's a Hamiltonian cycle. You ever play those games as a kid, draw this picture without lifting your pencil? Those are Hamiltonian cycles. So that's the game we're playing. But it's not just finding one, it's finding the one that reduces the total distance traveled. Does that make sense as a problem? So, well, how do you find the best solution? Okay, that's the big question. And you might say, well, here's the thing. The algorithm for finding the best solution is hilariously simple. It's hilariously simple. Create every possible path, pick the shortest one. Make sense? Entirely reasonable, right? So step 1 of the algorithm is, okay, create every Hamiltonian cycle, create every valid solution, every valid configuration, calculate their total distance, and then just after you're done that, go and pick the best one. Okay, great. Pretty easy. So we have to create every path, calculate their total distance. Well, okay, once I have a path, calculating their total distance, that's just adding it up. Okay, distance plus distance plus distance plus distance. That's easy peasy. If I have n cities, how many additions do I have to do? Like n minus 1, I guess, because I guess n because you got to go back to the original city. So n, oh, well, that's linear, whatever. So we have to do a linear amount of work for every possible path. And then we also have to say okay, well, we need to do a linear search through all of the possible paths. We have to do a linear search to find the one with the minimum value. Easy peasy. Do we agree that that solution makes perfect sense? I'm not playing a trick on you. There's no trick here. That algorithm makes perfect sense, and that algorithm is in fact guaranteed to find the minimal one. And if you're saying, well, prove it, it's kind of hard to prove. I mean, you just do it. Try them all, pick the smallest one. How do you know that'll work? I don't know, it just does, right? Right? So the problem then is, okay, well, I need to come up with every possible combination. So, I mean, let's think about it with this example, right? Let's try to think. I mean, you might have to go back to thinking like you're in grade 6 to remember how to do this, which I realize I've been joking lately, but that's easier said than done. Again, I'm not really joking. We have a total of how many different cities here? 1, 2, 3, 4, 5, 6, 7. Okay, so I have here n is equal to 7. Okay? Now, usually when we're talking TSP, traveling salesman problem, usually when we're talking about this problem, we always start with a fixed city. So this city is fixed. We are starting in Antigonish and we have to end in Antigonish. Okay, okay, fine. But I'm in Antigonish. How many paths are there? How many possible paths are there? Well, this is basic combinatorics. And you might say, I've never taken combinatorics. You bet your ass you did this in like grade 6 when it's like, you have 3 pairs of shirt and 2 pairs of pants. How many combinations are there? Who remembers how you do it? You just multiply it out. So, if I'm at this city, how many possible cities could I go to? Perfect. And let's say, hypothetically, I went to this city. Okay? So I'm here. I could have gone here, I could have gone here, I could have gone here. It doesn't really matter. But if I'm here, how many possible cities could I go to now? 5, right? Because we don't want to go back to where we came from unless we're done. We want to visit each city once and only once except the first city that we go back to. So it's 6 times 5. So let's say from there I went here. How many cities do I have left? Right, so we see the pattern. It's 6 times 5 times 4 times 3 times 2 and times 1, whatever. Right? Does anyone recognize this? What do we call that? Factorial, yeah, right? So that's here we actually would say this is like n minus 1 factorial, right? Because the one city's fixed, right? But, you know, we're lazy computer scientists. We usually just say like, whatever, it's on the order of n factorial, right? Right, so someone type into Google 7 factorial, 7 exclamation point, 7. See what Google says. 5,040. That's a lot of different possible paths. It's not too bad, but I mean, that's a lot. How many cities are there in Canada, do you think?
More than 7.
Probably like, let's say like 100, right? Someone type in 100 factorial. No, it's not. Times 10 to the 157. Woo! That's a big number. Someone go into Google and type in how many hydrogen atoms are there in the universe? Yeah. 10 to the 80. So there's like 70 times 10 to the 70 more. You could take 100 cities. Imagine I had 100 dots and I said, find all possible configurations. And I said, okay, take each possible pathway and take a single hydrogen atom from our universe and assign it. Over there. And you do it again. Hydrogen atoms. You're going to run out of hydrogen atoms hilariously fast. You won't even make a dent in the total number of paths for 100 cities. It's ridiculous. This is where big numbers become a big problem. So although the algorithm is simple, it is entirely unreasonable. Meaning, if you want to find a solution to that problem, you can't do what we would call the brute force strategy. Although it's guaranteed to work, how long would that take to run? Let's think for a second. So let's say, so what was it, 100 factorial times 10 to the 150. Okay, so 100 factorial. So let's say we could solve, we could calculate one path every millisecond. Or how about, let's say like a nanosecond, right? Or microsecond. That's like 1,000, a million. That's a billion times a second. Is that a billion?
That's
Nano? Let's say we could do a billion a second. All right, so, okay, well, what does that really mean? So divide that by, this is how many seconds it would take. Okay, 1 billion. Okay, one. Okay, right? Oh, yeah, that does nothing. That's how many seconds it would take. Okay, well, how many seconds in a minute? Oh, okay, well, that's how many, okay, look. Care for my order of operations here? Yeah. That's, okay, 60 a second, that's how many, like, okay, hours. No, minutes. 60, no, minutes, hours, days. Look, we're making this how many years? It ain't going to happen. Let's say we could do this many a second. It ain't going to work. It ain't going to work. Like, we're screwed. You can't find, oh, you can calculate 10 bajillion a second. It's still nothing. It's still nothing. That's how many years it takes. And then if you take this number and divide it by how old is the universe? Like 13 billion years old? 14 billion. Okay, let's say 14. That's how many, like, runs of the universe we would need. The point I'm making is, simple algorithm, yeah, but no. It ain't going to work. So if you so stupidly was like, well, my algorithm is fantastic, but if you don't take a moment to think about, like, well, what does it mean in terms of the amount of work you're doing, you're going to be here a little while, aren't you? Just wait faster. Yes, very good idea. Yeah, you'll hit run, you'll be like, oh, this is taking a while. How many of you have hit run on your code and it's taken like a second to run because you have to do a lot of work? Yes. And then you get to that moment of like, is everything okay? Right? I'm sure it's fine, I just need to wait a little longer. I mean, at what point are you going to be like, imagine you did have a bug in your code. And you wait like 10 quadrillion years and you're like, oh no, there's a bug. I got to start over. Yeah. So the point I'm making here is, to be clear, this is not a contrived example. Traveling salesman, this is a classic toy problem in computer science. It's not a contrived example. This is of the class of like an NP hard problem, which is a fancy way of saying it's like a pretty goddamn hard problem to solve. And funnily enough, if you came up with what we would call a polynomial time algorithm to solve this problem, when I say a polynomial time algorithm, I mean like an algorithm that doesn't take that long to run. We've come up with an algorithm that'll take that long to run. N factorial. Right? But yeah, if your algorithm is that, hope N is itty bitty. It's hard to get worse than that. But if you were to come up with an algorithm that's like, well, NQ or to the 4, that was able to solve it, you would be a very interesting individual. Because you would simultaneously be considered a genius and the bringer of evil upon humans. Because a lot of, by the way, like encryption and shit, is actually entirely breakable. It's trivial. Like, I can write the algorithm to break your secure connection to your bank every time you go banking. Like, it is trivial. Someone with your level of expertise could very easily write the algorithm that is guaranteed to break that encryption. It'll definitely break it in about that long. Meaning, well, look, It's technically vulnerable, but I mean, come on, it ain't gonna happen. It's these very difficult problems. So with encryption, they call it like a one-way function where it's easy to go one way, really hard to go the other way. Anyways, these algorithms are built on the fact that like there's these problems out there that are really hard. And it turns out this problem is actually, all the problems that are like NP hard that are really hard are actually the same goddamn problem if you look at it from a different way, which is a really interesting thing. But now we're getting to the weeds of like high idea computer science stuff. Point being, this isn't like, oh yeah, be mindful of my algorithm. No, this is like an elementary lesson in computer science. Be mindful of what you're doing. Who here in the lab did that two-sum problem? Find the indexes in a list that add up to a specific value. Chances are your first implementation was n squared, which is fine. Okay, n squared, it's fine. However, it's entirely possible to do it in linear time. And if someone shows up and says, I have a problem, I have a solution to the problem that's linear, and someone else says I have a solution to the problem that's quadratic, squared, the squared one, well, that person's an idiot. That's a bad algorithm. You're not an idiot for coming up with that algorithm. That particular problem is like your first introduction to like, hey, look at this, be careful. Anyways, very important stuff. So back to this. All right, okay, it's common to think about the worst case scenario for complexity analysis. Worst case scenario is the needle does not exist within the haystack. We're going back to the linear search. If the haystack is length 10, the loop will run 10 times before we conclude that needle is not there. If it's 100, it runs 100 times, 10 million, a million times, and it'll run n times. For space complexity, it only requires the space for haystack, so its space complexity is linear. That's fine, it doesn't grow. That's great and all. But you might remember last time I was putting a big emphasis on like how much more work how the amount of work changes as n grows. So even though it's like, well, maybe like on average, you'd have to look at n over 2 things. Yeah, but if I double the input size, I have to do twice as much work. That's where the linearness comes in, but that might be a nuance that's not overly important at this point. But I was careful about my wording. Now, I did do this before, right, where I showed you magically. Let's do it again for fun. But before I do it, I have a linear search. I need a volunteer. I want another volunteer, someone from the back. Who's brave? All right, you at the back. Yeah, you. Raise your hand, wave so I know you. I know, yeah, it's you. You're going to pick a number between 0, including 0. You're going to pick a number between 0 and 1,023. Okay? Think of it. Tell the person next to you so they know you're not cheating, that this isn't a, You got the number? Okay. We're going to do a linear search. Is it 0? Is it 1? Is it 2? How about 3? 4? 5? 6? 7? 8? 9? 10? 11? Is it 12? All right, well, how many guesses do I have to make to guarantee that I get that number? 1,024, because 0 was included, right? Point being, I have 1,024 things. Worst case scenario, I have to make 1,024 guesses. And think about why. Every time I make a guess, hey, is it 1? You say no. How many numbers have I eliminated from my search? 1. The number 1. But if you have a textbook in front of you, and I tell you, turn to page 512, and you open it, and you're on page 300. Okay? So I open a book, and I want page 512. Here's my book. And I'm looking at page 300 and 301. Right? Presumably I have like 300 pages over here, and maybe the book's like 1,000 pages long. Okay? So I've got like 700 pages over here. Right? I'm looking at these pages, but I'm looking for page 512. Do I need to look at anything over here? Why not? That's a stupid question because 512 is clearly bigger than 300. So the page 512 must be where? It must be on this side of the book. Unless the book is terribly numbered. It must be there. But by opening the book and making one guess, I open the book and be like, I'm guessing 512 is here. How many pages have I eliminated from my search? Well, I opened it to page 300 and 301. I know 512 must be over here somewhere. So I've eliminated the pages, okay, fine, 2 pages, 300 and 301, but I've also eliminated pages 0 through 299, or 1 through 299. Why? Because 512 ain't over there. So here, with one guess, I've eliminated a lot of potential locations of page 512. And this is a very similar idea to what we call a binary search. A binary search is like a perfect example of what I'm doing here. It's like the idealized case. So I need another volunteer. We've done it before, but we're going to do it again. It's you this time. You're going to pick a number between 0 and 1,024. Don't try to min-max them. Just pick a number. Don't look at him. He's trying to be an asshole. Just pick a number. Don't tell me. Tell him, though. And don't judge him based on his number, okay? You're going to? All right. All right. Now, I'm going to ask you a number. I'm going to make a guess. However, you have to concede one thing to me. You have to say higher or lower. That's it. That's the one thing I'm going to ask. So is the number 512? Lower. Okay. Is it 256? Is it 384? Is it 320? Is it 352? Is it 368? Is it 360? 364? 364. How many guesses was it? 8. I could have done it. I had 2 more guesses. Worst case scenario is it's 10 guesses, but with the number when it's bound by 1,024. Worst case scenario is 10 guesses. I knew I would have got it in 10 or less guesses. Now, if I asked, is it 0? Is it 1? Is it 2? Is it 3? How many guesses would I have had to have made? 350 whatever, right? 360, 364. 365 guesses, I guess, if I count 0. A lot more. But I was able to do it in less. And it's because every single time I made a guess, he told me, was it higher or lower? Yeah, higher or lower. And when he told me it was lower, I guessed 512. I knew the number had to be between 0 and 511 now. So I knew the number was between 0 and 511. A moment ago, I knew the number, the best I knew it was between 0 and 1,023. But I make one guess, and I've eliminated half of all the numbers. I make another guess, 256. That's the number right between 0 and 512, 256. With another guess, I eliminate half of the remaining numbers. Every single time I divide the number of remaining possible numbers by 2. I half it, and I half it, and I half it, and I half it, and I half it. That's the magic. That's where this search, a binary search, gets its magic. I can eliminate more than one thing with every guess. But there was a giant catch. The catch was I needed to know higher or lower, which in this example that translates to the data had to be sorted. In fact, somebody made a joke, was it you, about, I mean, unless the book has terrible numbering, and if the book had terrible numbering, I'm screwed, I can't do it. But because the book pages are numbered in order, I can play that game. If the data I had wasn't sorted, and now in the examples I've shown you, the numbers were 0, 1, 2, 3, 4. They didn't actually have to be like right next to each other. They just had to be sorted. Monotonically, no, not monotonically. Never mind. So the trick here is this binary search will always work if your data is sorted. If you have sorted data, you can search your data in better than linear time, which is phenomenal. Now, how much work is actually being done? And remember also that when we talk about computational complexity, we talk about how much work is being done as the size of the input grows, right? Like that's really what we're caring about. So how much work is being done? Well, with the linear search, if I had 10 things, I had to put my finger on 10 things. If I doubled it, I doubled the amount of work I was doing. To get a sense, now this one's a weird one because I know, raise your hand if you, here's the giant spoiler. Raise your hand if you learned about logarithms in high school. Yeah, just put your hand up. I know you did. Raise your hand if you're like, well, I technically learned about them, but what the hell is logarithms? Yeah, right, so that's most of us, right? To be fair, I was in the same boat, logs in high school, I'm like, what the hell is this? And then finally my teacher was like, it's like the opposite of like to the power. It's just instead of multiplying, it's like dividing. And I was like, what? Why didn't they say that? Well, because I had shitty math teachers, and you probably did too. Basically, when you do a log, you are dividing by some number multiple times, right? So if I do like 2 to the power of 10, that means 2 times 2 times 2, like 10 times, right? If I do log base 2 of some number, x, that means divide x by, divide 2 by x, no. How am I getting this back? My brain stopped working. It's because I shit on logs, and now the log gods are mad at me. Thank you. 2 to the power of what? So that's what it is. It's the inverse of 2 to the power of, right? So log of that should be 10, right? So it means divide multiple times. So a lot of times when we talk about binary search, a lot of people are thinking like, oh, that's like, okay, powers of 2 every time. If I double the input, it's powers of 2, it's powers of, yeah, but it's actually the inverse of that. It's dividing by 2. At the end of the day, a binary search is log base 2 of n. And by the way, almost always when a computer scientist says log, they mean log base 2. They don't say base 2 because it's almost always base 2. They would only specify it not being base 2 if it wasn't. Yeah?
If it wasn't ordered and you had to sort it first, could you, like, in step, do a binary sort with your binary search?
So you would have to sort it. There might be a weird way. I would sort it first and then do a search. Yeah. Now, how do you sort? Well, I don't know. We'll talk about that later. But this is a log base 2 algorithm. And if you have an algorithm that's linear, if you remember anything about logs, like look, let's say I said take 2 to the x, right? Don't worry. It might sound like I'm about to ask you a very difficult question, but just slow down. If I said, okay, take 2 to the x and then double it, right? Times 2. You, the genius that you are, should be able to, and if you can't do it, it's because you're too much in your head, If you can't realize, that's just, well, that's just 2 to the x plus 1. You just doubled it again. That means double 2 x times, and then double it again. Okay, double it x plus 1 times, right? And if we go back to the log idea, if I said, okay, two to the 10 is my input size. What's the log of that? Well, it's going to be 10, right? If I double 2 to the n, making that 11, the result of this is just like 1 more unit of work, right? It's whatever the power is. So if I double, if it's 2 to the 10, so let's say n is some number that happens to be 2 to the 10. Hey, who wants to type into Google what 2 to the power of 10 is real quick? Oh my God, it's 1024. Wow, I picked a number that was, anyways, do I say that? 10 guesses? Yeah, whatever. Anyways, but let's say n is some huge number that happens to be a nice power of 2 because we like simple math. So n is some huge number, and I double it. Well, whatever the amount of work was, log base 2 of n, okay, versus log base of 2 times n, is 1 more unit of work at the end of the day. The difference between the two is 1 more unit of work. The point I'm making here, listen carefully, is that with a linear algorithm, if I double the input size, a linear search on n elements takes n units of time. If I double n, it'll take 2 times n units of time. With something that's logarithmic, if I double n, it takes 1 more unit of time. And if that's unclear to you, imagine I said, no, I'm not going to guess the number between 0 and 1023. I'm going to guess a number between 0 and 2047, 2047. After one guess, what's my first guess going to be? 1024. The number between 0 and 2047. That number is 1024. You're going to say higher or lower. Let's say it's lower. You say lower. My next guess is 512. Oh my God, that's where we started off a moment ago. It's only 1 more guess. Do you see? Because in one guess, I can get to where I was when it was n minus 1, or half of n, pardon me. So if you have an algorithm that's linear to solve a problem, and you have an algorithm that's logarithmic to solve a problem, you pick the logarithmic one. Way faster, way less resources, scales way better. We love it. Any questions about any of that? All right, so complexity analysis of, okay. The magic with binary search is the data, I eliminated half of the remaining elements. 512, you said lower, so I know it's between 0 and 511. If you said higher, I know it's between 513 and 10,023. The idea is if I had n numbers to guess, and I guess the number n over 2, and I always continue, I continue. Every guess, I eliminate half of the remaining numbers, and that's all. But with linear search, whatever, yada, 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 this is just saying every set. Now, and I've shown you this before, I think, in lab. I don't know if I showed it to you in lecture, but I know I showed it to you in lab. This is kind of like a heading into next semester type of thing. So if at any point you're thinking, okay, we've been learning Python, great, but there's a lot of different programming languages out there. So, like, if I'm a programmer, I need to start learning all these different programming languages. Well, first of all, no, you don't need to. But second, you'll realize very quickly, if you continue to learn more computer science, that many of these programming languages, at least the very popular ones, are all basically the same. In fact, Python's kind of like the weird one in terms of like how weird it is compared to the other ones. But let's take a moment and look at what a linear search looks like. Okay. Also, try very hard to disassociate the algorithm and the code. Now I know at this point that might be difficult because every piece of code you wrote was an algorithm and every algorithm you wrote was Python code, right? But they are actually very separate. A linear search, the algorithm is start at the beginning, look at each thing, and if you find it, you're done. If not, keep going. And if I ever get to the end and don't find it, it's not there. That's the algorithm. We implemented that algorithm in Python with code that looks like this. Right? I've got type hints in here. Linear search, haystack is a list of integers in my example. Needle is an integer and it's going to return a Boolean. For I in range of the length of the haystack, if haystack at I is the needle, return true. Keep going, keep going, keep going. If I ever finish that loop and never return true, that means it's not there. That's our linear search. If this is surprising to you, you're in deep shit. This is a linear search. That is the code that is an implementation of the algorithm. But the algorithm was like the more abstract steps of how to do a linear search. This is an implementation of it. Now, raise your hand if you're like, yeah, I'm planning on taking 162. So if that's you, you're going to have to learn Java. And you're thinking, oh shit, Java's way different. And you look at this and you go like, yeah, that's different. And then you look at it for another second and you realize, wait, it's kind of the same. Look. Here is the exact same algorithm in Java. There are a couple of funny differences. I'll point them out right here. But the big thing is, okay, public static Boolean, what's all that? Don't worry about that. Exactly. But that Boolean, see the Boolean on line 1? That's the return type. Just like that return type, except in Python, you don't need it. It's the type hint. This is the return type of the function. It's going to return a Boolean. What's the name of the function? Linear search. It takes an integer array, it's like a list, kind of, but let's pretend it's the same idea, called haystack, and an individual integer called a needle. Now, unlike Python, where type hints are optional, in Java, they are required. They ain't hints, they are a statement of fact. So you need these things. But that top line, that's just the signature of the method or the function. The name of it, its arguments are parameters and their types and the return type. That's it. Public static, well, we actually kind of learned what public means already. But static, don't worry about it. We'll learn that next semester. It doesn't matter too much. And then what do we have? For. Well, that's a for loop, but this looks like a really different for loop. Until you know what it means, then you realize it's the same thing. For some integer I starting at 0. If I is less than the length of the haystack, do the stuff, and then once you're done, increase I by 1. You see the plus plus? You know how in Python there's plus equals 1? That's shorthand for I equals I plus 1. Well, plus plus is a shorthand to the shorthand. Plus plus means add 1. Because you know how like plus equals 5? Well, plus equals 5 works in Java too, but plus plus, it means plus equals 1. So it's like a shorthand. Neat. Anyways, yeah.
Can you do plus 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 if you're evil?
Maybe? I don't know. I don't know if the parser will accept it. I have no idea. I've never tried it. I'm not that psycho. I don't know. And did I tell you, did you know there's a difference between plus plus I and I plus plus? They mean entirely different things. I'll explain it another day. Anyways, this is the for loop. Some variable I, from where to where? Well, starts at 0. In Python, when you use range, it always assumes you start at 0. So what are we going to? Well, the length. Well, that's the condition. Well, I is less than the length. Increment I every time. It's a for loop. That's a for loop. And then what's the condition? Well, if haystack at I is the needle, return true. And if we ever finish that for loop, return false. So far I would say, okay, the signature is a little different, but it's still just the function signature. Public static, Boolean, it's the same thing though. Just, okay, you're telling Java, here's a function. Loop over the contents, Check if it's the thing you're looking for. If it is, you're done. If not, keep going. And if you ever finish, you're done. The algorithm is exactly the same. The code is a little different, although really it's not. But the algorithm is identical. It's the same underlying algorithm. Sure, okay, the if statements need those parentheses. And yeah, in Python we use indents. In Java we use indents too, but we use like the squiggly braces to signify what's in something or not. Other differences you might see is, well, why do some of those lines end in a semicolon? That's just required. No, we like that. No, that's a good thing. And okay, true and false start with lower cases, not upper cases, fine. Which actually makes more sense. Python's the weird one, but it's the same algorithm. I'm going to show you another language. Here's C#. You want to know something funny about the C# one? It's literally exactly, it is identical in every possible way to the Java one. It is, yeah. It's identical. So not only is it the same algorithm, it's literally the same code. And you'd be like, but it's a different language. It doesn't matter. That's what, when programmers are talking about different languages, this is like the level in which they're talking about different. It's not like French to English. No. Yeah, they're different. And there's nuance and whatnot when it comes to the language as a whole. That, you know, there's pros and cons to each language. But it's literally the same. Now here's C++. It's a little bit more different, but it's not. Boolean, linear search, this vector thing, well, that's the list. It's the haystack. We're looking for a needle. For I, from 0 to the size, okay, it's not like the length, it's the size, whatever. Yeah, it's a function now, exactly. Actually, it's a method, but yeah. So it's a method, but whatever, it doesn't, right? He's talking about the size, the fact that in Java and C#, it just said .length. That means it was like an attribute of the class. Where here, it's a method because it has parentheses. Good observation, but not overly important right now. But it's the same algorithm. In fact, the code is pretty similar to Java and C#. For loop, if statement, return true. If we ever finish, return false. Here's C. By the way, Java, Python, C#, C++, C, these are like the top 5 programming languages in terms of popularity. Don't quote me, they're fine. They're all in the top 10 at least. They're pretty damn popular. So I'm not picking I'm not cherry picking examples that are arbitrarily similar. No, these are like the big languages. And then we have like the big one, C. This is the magical language that like started everything the way it is. All of like your Python, C++, C#, Java, they all basically took inspiration from C. C is like you know. And the big difference here with C is that, like, unlike the other languages where like a list knows how big it is, in C, C's lists are stupid because they're not lists, they're arrays. You just need to magically know how long. So instead of like the list itself knowing how big it is, you would have to like remember how big that list is, basically. It is, but at the end of the day, isn't that like an interesting like motivation for classes? Wouldn't it be great if a list knew how big it was? Right? There's no classes in C. So we just have to just store this value somewhere else. If you haven't seen the point of class, if you were up until this point, you're like, I still don't see the point of having objects. But then you were to say, it's kind of annoying that lists don't know how big they are. You see the point of classes then. But long story short, we have that third parameter, n, which is the length of the list. And then we loop to n. Fine. Other than that, it's the same algorithm, it's the same code. Now, when people, though, there are languages that are quite different. For example, this is Haskell. Haskell is a different beast. It's a very useful, awesome language. It's functional. There's no such thing as a loop in Haskell. But ultimately, the algorithm the algorithm, start at the beginning, look at each thing. If it's what you're looking for, you're done. If not, keep going. The algorithm, it's the same algorithm. This actually is the same algorithm. But the syntax is kind of weird. Now, I don't think we really have the time to get into it today. If you really want, and you ask me nicely, I can explain it to you on Friday. But you ask like any experienced programmer who's worth talking to. Like this algorithm right here, it's hard to explain, but there's like an aesthetic to it. This algorithm, it's a weird thing to explain, but there is this like intrinsic beauty. Like this is actually like a beautiful algorithm. In a way, not like the other ones. Like there's something to this that's just so like, I don't know, there's this like wonderful aesthetic to it. And it's hard to explain, and if you know, you know. And I hope one day you will be able to look at an algorithm like this and see the beauty I see.
I can't believe Haskell is from the 90s and not like the 60s looking at that.
Yeah? By the way, this makes perfect sense.
It's like driving a retro car.
All this means is we have a function. It's an equation on something of type A that takes a list of type A and a thing of type A, and it returns a Boolean, obviously. What's the type A? It doesn't really matter as long as it's consistent. Is A an integer? Great. We've got a function on integers that takes a list of integers and an integer and returns the Boolean, the needle and the haystack, or the haystack and the needle. It could be Boolean, it could be strings. It doesn't really matter. But that's the top line. It's just the signature. Now the second line actually starts with a very interesting, the second line is actually like really the magic. And the magic is, let me put it like this. If you come to my office, no. How do I word this the easiest way? I'm going to give you a giant stack of exams, or I'm going to give you a stack of exams. So I need a volunteer. Who's brave? Somebody else. You're going to be brave? Perfect. I'm going to give you a stack of exams, okay? And you're going to tell me if your name is in that stack, okay? Now, understand that what I'm about to show you is not a figurative stack of exams. It is the stack of exams I want you to search through. And you're going to tell me if your name is in there, like if your name is on any of the pages in the stack of exams I'm about to show you. And I can't stress this enough. This is not a figurative stack of exam. There's no metaphorical stack of exam. I'm going to show you the actual stack I want you to look through. And you're going to be able to tell me like that if your name's in it or not. Ready? Why? There are none. Let's say you're looking for James. Okay, is James in this pile of paper on my hand? No. Why? There's no paper. So is it in there? No. How could it be? There's nothing there. Hey, is it in that emptiness? No. Hey, does this thing exist in a pile of things that doesn't exist? No. That's what that line means. If you ever see an empty list, and I don't give a shit what you're looking for, it's not there. And then you'll have to, spoiler for next time, because we're out of time. But yeah, I'm leaving you on a cliffhanger.